So thank you for everyone who's joining us today. We're very excited to have each and every one of you. So as you all may know, today our discussions will be with our CEO and founder, Achim Haug. Well, he will be shared about our newly launched global CO2 map, and he will also be talking about its features, its benefit, and how it can actually impact the climate actions. If you can see that Achim is already here. Hi, Achim.
Hello.
We're so excited to start the webinar, but I wanted to let you know that today the discussion is going to be a little bit different. So the flow is Ahim will start his presentation, and then the second we will have two different Q&A sessions. The first Q&A sessions will be dedicated to the topics of the webinar, and then the second Q&A sessions will be about some of the questions that each of you has submitted on our communication channel from our newsletter, our LinkedIn, and then our forum. And therefore, if you still have any questions that you wanted to ask outside of the topic, please feel free to leave it on the chat box, and then we will address it later on the second Q&A session. Great. Let's start. But before we start, I also wanted to let you know that we're committed in maintaining a respectful and constructive learning environment. So please take a moment to review our brief code of conduct shared in the chat box to make sure that we can run this whole webinar smoothly. Okay, so I'd say let's time to start. So Ahim, the stage is yours.
Thank you, Johanna. Great. Let me share my screen. Yeah, perfect. So, yeah, it's actually a really, say a favorite topic of mine, because very long, even before we started with the CO2 monitoring, I always felt it's strange that we have this discussion about climate change, and then we have the discussion about air pollution, and in the end, it's a very related topic. And then, and you will see the story in a second when we started experimenting with CO2 monitoring. It was just opening up this potential to really combine it. So what I want to cover today, little bit very basic, CO2 patterns. Then again, why we actually focus on CO2 a little bit, what our outdoor monitor is doing, what sensor it uses. Then we dive into how accurate is it actually, and then some real world examples and also potential future applications. Why this is really interesting. So for CO2 patterns, I think some of you probably know some of these charts, but I want to start and go very much back into the history, and we look at the last 1 million years. I think some of you probably know that chart. So over the last 1 million years until the Industrial Revolution started, we were always like pretty much below 250 or 300 ppm CO2, and then you see like just what happened over the last 100 years plus years. No? So obviously that's very striking. So that's a 1 billion years view. But if you dive in a little bit and just look at the last 60 years, that's when more accurate measurement was done. We see some interesting pattern. Obviously it's going up, everybody knows that, but we see these seasonal patterns. So it's interesting to dive into this. And these are all really interesting charts from the NASA website. So they have these, I think in Hawaii on the mountain, Mauna Loa, that CO2 measurement station, and then we can actually see how it changes throughout the year based on like the growing season. So we know when plants grow with photosynthesis, they basically convert CO2 into oxygen, so the CO2 levels drop. And then when it's more in winter time, it basically, or fall, it's basically going up and so on. So that's an interesting pattern, which we not only see throughout the year, but also actually throughout the day. So this is actually a chart that's from our monitors, where we can clearly see during nighttime CO2 increases, and during daytime it typically decreases. And I think that's really, really important to know, because often when we actually at AirGradient, we get customer requests and sometimes say, hey, like I put this outside, I know it's 430 something, but it measures, either below or up. This thing is not accurate. So it's really important that this global increase in CO2 levels, it's really an average across the year, across basically the whole globe, and really an average of all the emission source. And that's really, really important to keep in mind. So you will have, and you will see that later on, especially in the countryside, you will see very, very high fluctuations on natural CO2 levels. So going in here, so what are the sources? We all know, with the Industrial Revolution, we were burning a lot of fossil fuels, coal and oil and so on. And there are a few other human-made sources. Deforestation obviously is the counter effect, because we have less photosynthesis basically, but also things like agriculture, waste management, also the whole cattle and so on produce a lot of emissions. But then we also have like natural resources. So these were the sources that were actually before, like if you go back this 1 million years, we saw certain peaks. And that could be based on volcanic eruptions, for example, that could just push up a lot of CO2 into the atmosphere, or maybe large-scale wildfires, for example. And then obviously also human livings, animals and so on are breathing, which is a natural source of CO2. And there's also an exchange between the ocean and the atmosphere. But looking at the pie chart on the right, we see actually that nearly 75% is basically on from energy production and use. That's the main contributor of CO2. I think that's all pretty clear. So it was just like opening the stage a little bit. So why we focused, and I mentioned it early on. So this link between air pollution and climate change was always like really, really important for me. And to also like just leverage the awareness between the two. Like, for example, I grew up in Germany, which doesn't have as bad air pollution as in Asia, where I live now. So it wasn't really an issue. It's still not that much an issue, I would say, compared to like highly polluted countries down here. But obviously climate change is a global issue. So linking these things together, I think, will create a lot more awareness, and also makes it more. And I think that's a really weak point. What we see here, for example, in Thailand, we have this pollution season. Everybody's concerned doing something, and once the rain comes and the pollution drops, everybody's happy and like forgets about air pollution until the same thing happens every year again. So having this constant attention on the issue through climate change really helps driving improvements to a big extent. So that's why I think it's super important to combine the two. But we also have additional benefits we cover in a second here. So I talked about awareness, and the other thing that we will cover here primarily is basically how this hyperlocal measurement of CO2 can really reduce emissions by basically identifying the source, where it's coming from, and then also comparing the developments of CO2 over a longer period of time, and see, are we actually reducing or eliminating these emission sources, which then a lot of these things in combination will help fight climate change. So diving a little bit into the open air, that's our outdoor monitor, which has the CO2 module. It's basically behind the PCB here. We will cover that sensor in a second a little bit more, but we also measure PM 2.5 through the plant tower PM sensor, which has an included temperature and relative humidity sensor. And then we also have TBLC NOx sensor, which I think is still experimental to some extent. So we are still doing a lot of co-location studies there to see like what can we do with the data. We are also looking into more expensive NO2 sensors that could be more accurate in future. But today we focus on CO2. So this is the module that we use. I think a lot of you guys here in the webinar has built one of the outdoor monitors. So it's a sensor. That's the company. It's a Swedish company. The S8 it's a pretty, I would say, pretty good sensor from the quality. So we compared a couple of other CO2 sensors, and on the low cost range, this is actually one of the best. It measures from 400 to actually up to 10,000. It's more accurate between that range, 400 to 2,000 ppm. But now, especially if you talk about outdoor measurements, outdoors you will never be above 2,000. So how does NDIR sensors work? So this, I think, is important to understand. And what it basically does is, so there's a chamber with an infrared light, which is tuned to a specific wavelength. So for CO2, you can see that it's basically 4.26 micron. And basically then the light is absorbed on that wavelength based on different gases. So if you have a receiver here, and that molecules absorb that light, so we can then see on how much we measure on the receiver, basically how many molecules are in the air, and that's how the CO2 is estimated. And then you can see, like, basically based on that wavelength, you could also potentially measure other pollutants in the same way. So I think it's a very, like, let's say compared to PM 2.5, which uses a laser and the scattering methodology, I think it's a very precise or more precise way of measuring gases. And this is also why often when, like, in our test chamber, we can like test, I think, 100 monitors at the same time. So once we calibrate and set the baseline at exactly the same level, you cannot distinguish the curves anymore because they all behave exactly the same way. Now let's go on accuracy, and I think now it's getting a little bit more interesting. So we started like last year with beginning of last year with the University of Cambridge to do a little bit of research to look at how accurate can this little thing here, and this is basically a really size comparison, compete with a reference CO2 station. And it's a portable one. It's a Lycor, which is 10 kilo. I think the sensor S8 is 8 grams, no? Just to give you a comparison. Similar measurement range, but obviously like probably 1,000 times more expensive. No? And so this is really like a device where you can really measure these atmospheric levels. It uses a so-called cavity-enhanced absorption spectroscopy, and that's actually in a way, it's a very similar method like the NDIR, but they use some optics, some mirrors to basically extend that kind of length that they measure, and because of that, it becomes more accurate. Additionally, also they can condition the air that goes into it, so they can put it on the same like humidity level, same temperature, and that also obviously helps in the accuracy. So how does the setup look like? So we have actually 2 stations, and first we look at the rural one. So that's somewhere in the countryside in England. So you can see here there are like 5 open air sensors from us with the sensor S8 module, and then in this box here is basically that reference station. And if you look at the data, and the data that are shown now is really the raw data. So there was no, like, they call it out of the box data. So you can see here the reference station, the big unit is the red line, and the blue one is basically the our unit. And you can see that it's this is 2 weeks. First, interestingly, in the night, actually the CO2 can go really, really high. You see up to like 800 ppm. I didn't expect this, but then I did some research and it's really possible. Basically, it's because of all the plants and the nature. There it can go that high, but then there are also periods where it's actually low. This could be based on meteorological condition, wind, and so on. So we see quite a lot of fluctuation. So what's interesting here is basically that if you look at the data, we see an RMSE, that's the average offset between the two. So on average, there's like around 13 ppm difference between the red line and the blue one. But what's a really fantastic value is basically the R. And that basically tells you the correlation. So if an R of 1 is like a perfect correlation. So we have an extremely high R, and that's actually what the scientists are more interested in, because the correlation, like the offset, you can much easier compensate or calibrate, but not the calibration. So this is a very, very positive result here. And then if we plot this on an XY chart, so this is also where you can easily compare the reference here and the gradient sensor. And basically you have the black line here, which is the 1,1 line. So if both units would show you the same value, let's say 400 from the reference and 400 from us, it would be exactly on that dotted line. Okay, so this gives you also a really good idea on how accurate this is. So the closer it is to the diagonal line, the more accurate or the more agreement between the reference and the outdoor unit we have. So let's look at a longer period. So this is the same data over 2 months. It's a little bit different formatted, but basically very, very similar. So we have an R square this time, not an R, but the same result. I think 0.99 squared, probably 0.98 if my math is right. RMSE a little bit higher here, 15, but also very good correlation. Now let's look at the city. So this is at the University of Cambridge on the roof of the Chemistry Institute. So you can see there are 4 open airs, and then they have basically the unit inside, and then they basically have this pipe that basically then sucks the air into the reference station, and that's how they measure it. Yeah. So in urban levels, I think the first big difference we see it's the variation is much lower. So obviously you have a more constant CO2 levels because you don't have this kind of natural effects from plants to that extent. So it's pretty much just varies between 400 and 500. And probably because of that lower variation, the R square is a little bit lower. RMSE is similar, but this is also out of the box, so there has been no calibration done. What's interesting on the longer perspective, here's the one line, very similar to the outdoor one. What's interesting here, and I marked it already with the ABC effect, is that we have a little bit an interesting pattern over the 2 months, okay? And you can see here, it seems like there are kind of like 2 lines or even 3 lines kind of in parallel. And this is due to something called automatic baseline calibration effect, okay? And this one impacts the R square to a big extent. And the good thing is that this can be pretty easily avoided. And I want to first explain the automatic baseline calibration effect. And this is basically how all low-cost CO2 sensors work, or how they calibrate it themselves. Is basically they look at a certain period into the past and then assume, let's say, for example, the sensor SA, the one we use, looks at 7 days and then says, what was the lowest value within the last 7 days? And then it assumes that's like an ambient level of 400. Okay, it should be 400 probably, but they assume 400. And then every week basically it looks at the past week once a week and then just resets itself to that level. So if the lowest level was basically somewhere here, it will basically look at how much does that deviate from 400 and then subtract that amount, and then it was just jump down. So it makes certain steps. No? And I think if we go actually back to here, I think we can see this. Yeah, it's a little bit, I think here's probably a step and somewhere here. So we can actually observe that step. So especially if we look at longer periods of time, for sure, we have these steps and these are creating these effects here. And probably because in the rural area, we have more variation. I believe that we don't, like it just calibrates better with a higher dynamic range of the CO2 situation. So let's wrap this up a little bit just from the accuracy point of view. So what's good? We have very, very high correlations, which I think is amazing that we can actually compete with an instrument that's, I don't know how many times bigger, but 1,000 times more expensive. What's not so good is, we have an offset. So it's not useful to say, hey, we want to really measure 435 ppm and see exactly how it goes up in the atmosphere. I think that's not possible with these low-cost CO2s. We also see that the ABC disrupts the measurement and that it's working better in the rural environment. So what we can see, basically what I said, like it's useful to detect patterns, short-term, medium-term changes, but not useful for these atmospheric levels. Now, let's look at some real-world examples. And so the good thing is we have, I think, 700 or 800 CO2 measurement public monitors on the map. And then I went into actually onto our public map and just looked at certain spots in the map. And I found one actually interesting monitor, which is on a pier in Bangkok. And that was actually one we donated to daycare centers in Bangkok. And apparently there's a daycare center on a pier. I want to go there sometime. So what's interesting is I think people that have been to Bangkok, they probably saw these kind of speedboats running on, they call klongs, which are these camels. And you can already see like at the back how dirty it is from the emissions. So these speedboats are notorious dirty pollutants. So it was interesting to have a monitor just next to the pier and look at the data. And I think what's also really important is they only operate during the daytime, basically. So it's a lot of commuters use them to go to work and back. And obviously during rush hour, they run more frequent. So if we look at the data here, we see some really interesting things, both on the PM side as well as on the CO2 side. So we see during the running, so this is like a 48-hour snapshot. So we see during the daytime when the boat's running, we see really a lot of spikes, basically, and in the PM, and very, very interestingly also on the CO2 side. So then I said, okay, let's compare the same time, the same 2 days with, let's say, a place in Bangkok which is more quiet, I would say. So I found another monitor with from a community member running in a small street that's actually so small that no cars can enter. And then Google Street View gave me that picture here. So that's probably roughly, I don't know, maybe 10 kilometers away from the pier. And if you look at exactly the same time frame, we see a less noisy picture. No? So we can see here also the PM, the CO2. If we look at, there are like two spikes here in the middle of the chart. So if we go back actually to here, we can see and look at the scale. So this goes up to 120, this one to 35 because we don't have the spikes. So if we look at the pier, we can actually see these two spikes here, and that's called background PM levels. And then on top of that, we see that emission spikes only on the pier, but we don't see them in that quiet street. And the same pattern, we actually have the same background levels we have here on the street, basically, where we have this typical pattern that in the night it's going up, and then during daytime it's going down. So this is some really, really interesting information, because we can clearly attribute these spikes, and we can actually measure them. We can quantify them with the boats. No. So what can we use it for? So actually, like more than 10 years ago, there was actually a research on exactly that transportation with the boats on Lake Long and how unhealthy it is. And in the results, the researchers made actually a really interesting statement. They say it's highly variable as a consequence of individual boat state of repair. Okay. Now, this means that boats that, are not, the engine is not fine-tuned, they might have certain injection problems that, as a result, will have much higher emissions than tuned boats. And we know that because all our cars normally have to check for emissions, and then the engine is fine-tuned. So actually, this could also be used if you compare it with a timetable and you see which boats are actually passing by. You could probably detect boats that have more problems on that side and need fine-tuning of the engine compared to others. What else it can be used? So there's a discussion, or there's some trials in Bangkok to actually electrify these boats. And obviously, measuring this would really help to see, like, do we actually reduce? How fast are they introduced? So if you then look at the number of spikes, for example, you can then easily see if that's a successful reduction in emissions, for example. Good. So let's look a little bit on some hypothetical other applications. And what we have is there's more and more discussion, obviously, and it's already done. We store carbon dioxide underground. So often it's part of, okay, we take oil out, for example, and then we have some kind of holes in the earth, and we could potentially pump in CO2 to store it underground. So what happens if actually there's a leakage? There's like studies out there. This is just a picture I took from the internet, and you can see here, hey, like, yes, there's a potential with fault lines in the earth that actually the CO2 then creeps up and somehow then gets out into the atmosphere, and that's not where we want it, obviously. So if we had a ground-based dense network of low-cost CO2 monitors, we could potentially detect these leakage areas, and then people could go there and try to fix them. I think another interesting aspect is, and that's also some research going into the directions, what kind of plants are actually more effective in taking CO2 out of the atmosphere? And so you could use a dense network in different types of fields to basically look at how basically performant are different plants in reducing it, and also understanding a little bit like there's another research area looking at when the soil temperature actually rises and the microbes in the earth, like to what extent they emit more CO2 actually. So there are some effects that people don't really understand yet. So this is another thing to look in. And then obviously we know agriculture and like also cattle, like variable like pigs and cows and so on is a big contributor to CO2. So having these measurements in the nature can actually give us a lot more information here. So what are the takeaways here? I think we see very good accuracy with the low-cost sensors. We can, I think, clearly identify local emission sources. And this can also help. A lot of cities are now basically creating emission inventories. So they look at, okay, what are the main pollutants in my city? And obviously it's easy for certain areas, maybe like power plants or certain factories, no? It's probably easy for them to quantify that, but then there are other areas which maybe is more difficult. Let's say the boats on the Klong, or if people burn their rubbish in it's one of my neighbors here doing like every Thursday, or stuff like this. So that's where I think these low-cost monitors can help. And then I think also on the awareness part, it can really help. Just citizens can actually engage the same way they do on air pollution, and trying to detect these emissions and uncovering them and sharing the data, and then allowing targeted interventions basically to reduce them. Obviously, there are quite a number of challenges as well. So I think one of them is that, especially for the CO2 measurement, I think the monitor needs to be very close to the emission source, which is often not possible. You need then to obviously build up a very dense network, especially if you want to get a very comprehensive picture. And I think also something that's often not enough on the radar is in order to detect these spikes, you need actually high frequency data. So like when I showed you the spikes from, let's go back here, from here, this is like 5 minutes aggregated data, which is probably already maybe too much aggregation. So it would be interesting to see how does that look like with 1 minute data points, because I would imagine that the 1 data points, you would have more spikes and they probably would be a lot higher. Okay. Now imagine you have a monitoring network that's only measuring maybe hourly, or gives you hourly average. So then probably all these spikes would have been disappeared. So the frequency of the measurement, I think, is super important here. Good. So the CO2 map is here. Let me see. Yeah, that's actually my last question, last slide. So if you go on our website, you can go to map here, and then you can switch here to CO2, and then you can have a look at Bangkok, for example. Here. Yeah, and then you see, for example, you can actually see that monitor that we was just talking about here in the client. See if we can get some PM spikes or not. Yeah, so same picture, it's still there. We can see these spikes here. So yeah, and this is like basically, let's just switch off my presentation for a second. Yeah, so this is why like we launched a map where we feel there's some really interesting applications or use there, and something also that's, I think, pretty new from, let's say, a low-cost CO2 standpoint or citizen science, or that people can really engage and measure that. At the same time, I think it's still a very open playing field. So like a lot of these use cases that I indicated are still, I would say, developing. It's not as clear cut as, let's say, with air pollution, but this gives, especially from that kind of crowdsourced perspective, I think a lot of potential to really dive into the data. And you know that we are open data, so people can use that data, can run certain models on it, and hopefully they can contribute to help in detecting more, let's say, emission source, and finally then reducing them. Yeah, that's from my side. I'm not sure, Johanna, if there are certain questions in the chat.
Yes, thank you, Achim, for such a detailed presentations for tonight. I have already seen some of the questions on the chat box. We can start with the question from Niels Kaiser. Back to the quiet Thailand street. Why is the CO2 building up at night outside? I only have a CO2 sensor on my indoor monitor where I always attributed CO2 buildup due to closed windows and AC.
Yeah. I think it's like what I think it's quite different if you measure CO2 indoors and outdoors. So obviously, yes, because it's a very confined space indoors. So very, very quickly, if you don't have a window open or you don't have any like ventilation system, it's just creeping upwards. And there's also not too much normally in a room, like you don't have that effect from, let's say, from plants that create oxygens or trees. You don't have the effect from wind that kind of blowing away or mixing the atmosphere. So it's a very, very confined space. So you typically have kind of like a lab condition indoors, I would say. And when you measure CO2, whereas outdoors, you have all these influences. And so why is the CO2 building up at night? I think it's this general pattern that I explained at the beginning, is that there's no photosynthesis. Obviously, there are not that many plants in the street as well, but Bangkok is surrounded obviously by countryside. If there's wind blowing, so you can see this pattern that CO2 increases in the night and decreases during daytime, also like basically everywhere. But in the cities, it's just less fluctuating, and outside in the rural, it's higher fluctuation. Yeah. I hope that answers it.
Okay, thank you. The second question is from Victor. Hi, Ahim. There used to be a layer on the AirGradient map showing wind speed and directions. I think it would augment the ground level reading comparisons. Is it still possible to access such a layer?
Yeah, actually, it's a really good question. And so we actually kind of reprogrammed the map completely a couple of weeks ago in order to integrate it into our website, and we had some performance issues. So step by step, we will bring these old features back. So wind direction is one of them. Another one is that we also had a layer with the wildfires. These hotspots, there are satellites from the NASA and I think the European Union that basically detects these hotspots. And this is super interesting additional information to have in order to, for example, also see like how does the wind direction and the wildfire influence, like kind of it's blowing into my direction or it's blowing the opposite direction, to also make certain judgments where you should go and in order to reduce your air pollution. Yeah, so Victor, this is definitely coming back.
Okay, I don't see any other questions for the presentation topic. Do you want to go to the next Q&A sessions, perhaps?
Yeah, so I share one second. Good. So we didn't have too many questions coming back. I have two here, and I go on the first one. So with Apple HomeKit and Meta integration, so we actually have and I put the link in here. So for HomeKit, we actually had a contributor from the open source side that actually integrated that into HomeKit. And it's not an official integration. And for Meta, I think, at some point we probably going to do it. I think it's something we kind of still observing. Meta has a pretty high fee for certification if you want to like as an official manufacturer doing it. But it looks like it's really becoming a standard, and it would make integration a lot more easy. So I think it's likely that at some point we support this. At the moment, we are looking more into supporting like other like more open source projects. So we have an official Home Assistant integration that we just launched like a month ago, which is now integrated in our firmware. And then actually we just launched last week Homey. That's another smart home system integration that works. So more and more integrations are coming. So I think, yeah, Meta and maybe even an official HomeKit will probably be coming as well. Now, another question we got was, and I think that's a really good one, is like, I'm having a really hard time picking an indoor air purifier. So it actually reminds me like, living in north of Thailand and having this wildfire and this like massive smoke situation. I was also like, I think before I really got into the topic, like, okay, like you have the smokes, the wildfires, like also what's going on in California at the moment. And then you go into a shop and they're like 20 different units from all types of price levels and telling you about like, hey, this is like some ionization feature or this or that. And you don't really know like what to use. So the interesting thing is that the same like that we actually promote like DIY air quality monitors, there's the same thing for purifiers. And I just put in two links there. And they actually, so one very famous one is called Cozy Rosenthal box. You can Google that. I think it's from the University of California, Davis, a professor that invented it. And it's basically just you go into a home improvement shop, buy some standard HEPA filters and a box fan and use some duct tape and then basically put this and they are actually very, very performant. So they can keep up with air purifiers that cost you hundreds of dollars. And then I think another company, Smart Air, started doing this in China, also as workshops. Basically, they also sell like a DIY kit, just like a HEPA filter, and then you have you just strap it around. And I actually did the same thing. I used these cylinder, I think from Xiaomi, they have these HEPA filters which are round. And then I just put a duct fan basically into it and had a very performant purifier system. Yeah, something like this. So it's actually, it's so simple. So maybe just to wrap it up. So for air purifiers, HEPA filters work. Ionization doesn't really work and it's potentially unhealthy because it can create ozone. So just get a good HEPA filter. The bigger this filter, the better, because it just doesn't clog as easily. And then I think you also don't often need the highest grade, because with the air, like especially if you build something like this, you are basically recurringly like pushing the air through the filter. So you don't need a filter that has just one pass and gets it down to zero, because you have basically recurring circles. But I would still recommend a good quality filter. And then just, and it's just basic physics. It's just, you have to basically drive the air through the filter. And so you can save a lot of money with this. If you want to buy a professional air quality purifier, I would just say, stay away from all these ionization stuff. Look at basics. I think the noise is very important. In general, I think the bigger the better, because then you can run it on maybe it's just the medium level. It's not as noisy. It still gets a lot of air through it, and that's basically I think the key points. Yeah, that's what I have. I don't say bye bye yet. Are there any more questions or any?
Yeah, I think we could go back related to the questions we have before in the first Q&A. There's a question from Heroin. If you would indeed have a wind data, what would be the required density of or resolutions of monitors to effectively find pollution sources?
Okay, that's a really tough one. I don't really know, to be honest. I think we would need to experiment. What I understand from looking at meteorological data, that it really depends on the topology. Like if you have, let's say, just a plain field, like let's say Holland, because I think the question is coming from Holland. I think you probably need less. If you look at some, like valleys and hills, or maybe inside a city with a lot of skyscrapers and stuff, you probably have a lot of like turbulences, which would probably like impact the wind speed. And also one thing we are very early on in that. We would probably also need, there are a lot of third-party providers for wind speed. So it would be interesting to actually, for example, that layer that we can pull into the map to better understand how accurate, and if we zoom in on a very detailed level, let's say on a block level, is this data still accurate or not? Because often also if it's satellite derived data, I know this from there are satellites that actually estimate PM 2.5, and I know from Thailand it's totally wrong. So often there's this problem that, yes, it looks nice, it's nicely animated, but often the data is not very accurate. So I think we just need to look into this. Sure. Hope that answers it. Good. Johanna, we have another one.
We actually have a comment from Paulo. Our experience is that the web data from high altitude satellite, we need more ground level data. So probably that will also add another data combined with the ones that you already mentioned. And I think that's all of the questions we have.
I think I see something more. Okay, Melon made a comment. Some creative ways to reduce CO2. Okay, perfect. Then we had Sharon. I just answered. Okay, this is interesting. Yeah, maybe with some kind of bridge. I was thinking the same, with Meta. The good thing is because we are so open, we build these integrations also with Home Assistant. We can basically jump then through another system into Meta. It's definitely something we over the last, I think until 2 or 3 months ago, we completely rewrote the firmware of the monitors. And now it's really, it exposes a local server. It's so easy to, I think that actually the Home integration took us 1 week to do. It was a volunteer from the community who did it. So I think that the base is there in the firmware to very, very easily make integrations with other systems. So I think there's a lot of potential there coming up. Then Victor. Okay, I think the layer we addressed already. I don't see it.
We have a question from Victor.
Yeah.
Are there future developments for standalone air gradient sensors? It is sometimes difficult to set up to areas with limited Wi-Fi.
That's actually a really good question, because I actually had a picture in the presentation with a solar cell and a cellular modem. So we actually we produced a couple of hundreds already. They're still a bit in the testing phase, so they are not officially available, but they work pretty well. And so what they have is, it looks like the normal outdoor monitor. It has a longer antenna, which we might also put inside the enclosure. We're still experimenting with different antenna types to make sure the reception is good. But basically we have two different versions there, because we have this problem that some countries, for example, actually Holland is one of them, and I think Switzerland is another, that they already switched off the 2G network, the GSM. It's just not working anymore. And everything is on 4G or narrowband IoT, no? Now, and then we have the opposite, like if you look at countries like Indonesia or maybe Philippines, no? You don't have anything of the new networks, but the old one is still running. Okay, and it's a completely different technology. So what we actually finally decided, and that's why it took us a little bit of time, we have a cellular modem now that actually has both versions on it. So we can actually then really roll it out into, all types of countries. We are not limited to the 4G or the GSM that can run on both. But this made the whole thing a little bit more complex. So we are still testing it, and we also want to make sure we only sell something if we are like 100% sure it's really running stable. And you can imagine there are potentially like 150 countries it could run. Often SIM cards are not the same. The SIM card is not the same like this SIM card. I mean, it's just way more complex than like a Wi-Fi module, for example. So yeah, we are still testing it, but it will definitely come in the units that we have running already in a couple of countries. It looks really good, and I think it will address a major concern. Actually, not only outdoors, we also have big studies. Like, for example, when we did studies in the UK for indoor air quality, often it's not that easy to actually connect it indoors. If you, let's say you make a study with low income households and you tell them, hey, like here's a monitor, we want to measure the air quality. Like it's just a lot. It would be much easier to just give them a device, they plug it in, and then it sends data than having to go through some kind of wireless setup. So it's not only for outdoors, we're also looking at for the indoor monitor actually. Good. Anything?
Yes. One question is from Harry. Will the autonomous solar powered monitor include battery backup for low light overnight conditions?
Yeah. So at the moment, what we do is we use a third-party solar module from a company called Voltaic in the US. It's really good quality. I think the only downside is I think it costs more than our monitor, which is obviously not ideal. But this one has a built-in battery. So we are looking actually at lower cost alternatives. We might also come to the point where we actually produce one ourselves, because then we can, make the enclosure fit better together, for example. And this will definitely have the battery inside. Yes, we need to make sure we can continuously monitor, 24 hours, also cover then, like cloudy days, winter times. So make sure the panel is big enough, the solar is big enough. Yeah. Good. Is there anything? I don't see anything.
Yes, I also don't see anything else. Perhaps maybe we can end today's discussions, but wait. Oh yeah. But perhaps before we close it, do you want to give any of us closing statement on what's the future updates or closing statement from your presentation?
Okay, great. Johanna, you got me there because I didn't prepare any closing statements. So what could be, I'm super excited. That's actually why I wanted to hold this personally. I mean, we have actually a few scientists at AirGradient too that's actually working on that topic too. But it's really something that's coming from like our heart, I would say, that we say, hey, look, we want to really make a difference. We want to like not just make a product and then people use it and see some data. We want to really see like how can we actually improve the environment basically. And so when we got the first results, I still remember very vividly like more than a year ago with how well actually these low cost CO2 sensors work in the wild, because I think before nobody really tested it. No, I was really like I thought, okay, this is really cool, and this is why we also call the open air outdoor monitor the climate change monitor. Obviously, it's a kind of stretch. Thank you, Sharon, for showing that. Yeah, but for me, it's really a yardstick. It's like, hey, like we want to really roll this out, make it as accessible as possible. Get the data. Even at this point, we have some ideas how it can be useful, but I think there can be a lot more potential if we just get more data points, have the data public, has the research community actually helping us in how to analyze the data, and then like really maybe form even like, community action groups out of this and say, hey, look, I detected this emission source here at the pier. There's actually a daycare center. I mean, that's what we have to think about. There are like young children actually on that pier that breathing that air every day. So let's do something, So it's really opening up this power to use data for improvements. Okay, good. Was that a nice closing statement, Joanna?
I guess so. I see that some of us noted. Okay, great. Thank you so much for today's presentation. And I think let's give a virtual round of applause for Ahim for the insightful and very detailed presentation. And also on behalf of the entire Air Gradient team, I will want to say thank you for each and every one of you for joining our webinar today. So see you on the next webinar. Goodbye, everyone, and thank you.